Okay, so I kind of introduced myself earlier, but I'm the software engineer who wrote the real-time observing code and also manage the observatory up there. So wearing both those two hats, I find a way to introduce lots of features and bugs into the data. And we'll talk about a few. It's a movie that you may or may not have been watching while we were sitting and setting up is the degree of linear polarization for I think all the data we had in 2022. And you can see some really boring stuff, like these coronal features, and I think that might be a lagomorph, and there might have been a coronal hole go by. Ignore those. Over here on the side, there's a bunch of scattered light coming in. I don't know what that was, but that was cool. There's going to be a bright feature over here. There's going to be another feature over here. So even this was a process recently, but this is our best guess of what the pipeline could do. And we're still having a bunch of features and artifacts in the data. And I want to kind of go through and give an overview of kind of what we think we see, what we think are potential issues, and try to give some hints and techniques on how to identify some of these so you can exclude them from your processing. Ideally, we're going to try and fix them, but if the level 0 data is bad in some way that's not processable, we're just going to have to get rid of them. And the one thing I found when digging through a bunch of this data was this azimuth plot that looks like we got a fire-breathing dragon over here. So this was a problem we'll talk about in a little bit, but it went into the daily average. Azimuth's not the exact data product over here, but it's part of the polarization that got into whatever frame in the movie that was. Okay. So Steve and Mike kind of went over this, but for our data, we combine a lot of images in to get what we're going for. So our typical Synoptic data product takes about 2.5 minutes to collect. That's what we've been doing for the bulk of 2022. We do 3 wavelengths across the emission line. This gives us our 4 Stokes vectors. And to do this, we're end up doing 3,072 raw camera reads, of which 1,024 are per wavelength. So on a per wavelength scenario, 512 of these images are on band, 512 are off band. A quarter of them are for each of the sort of raw modulation polarizations, which, as we noted earlier, are not IQUVs. They're something that can be combined to IQUVs. So if we do something unfortunate to the telescope while we're going through this 2.5 minutes, every one of the IQ, and V for a particular wavelength are going to see that unfortunate thing because they're all coming from the same 1,024 source images. I was talking to a couple people here earlier, and they're trying to say, okay, earlier this week, which image exactly produces this? It's like, no, all the 1,024 source images produce all 4 of these. The polarization's encoded into all those, and we dig it out the way that Mike showed us in the previous talk. So this is just a kind of graphical overview of what we're doing. When we're doing our Synoptic, we're looping through 3 different wavelengths with the 2 cameras taking turns being on and off band. So this, in a Synoptic, we'll do this loop 4 times, and we're doing a bunch of reads. So if this read was bad here, all the wavelength number 2 is going to look bad. So it's, there's a lot of places it's going to come at. Just another way of showing what we've talked about last couple talks. So with that kind of out of the way, I just wanted to touch back on our signal. So most of what I'm going to talk about is the noise, but the signal for Yukon, not just the camera, everything's optimized for the 10.74 kind of range, the R13s. So you can see the black line here is the overall internet throughput. It goes down to like 4% at 530, and it's like 12% where we're looking good. And here's kind of a plot that Steve alluded to earlier. The green for all of our lines is basically the line width we expect from the sun without any Doppler broadening. And then the yellow is the on-band tuning, and the red and the blue are where we would do our other 3 points. So in 530, most of our data collection is missing most of the photons. Plus, the Leo filter gets rid of them. So all this combined, our data, these were the same from the same Synoptic program, 2.5 minutes each. You can see a lot more coronal structure in the 1074 and 1079, maybe a little bit less than 789, basically nothing in 706, and kind of noise in the 530, 637 or something. So as we go more into the blue, the signal goes down. So then the kind of categories I'm just going to run through our noise sources. We have this interesting wavelength drift. We have some issues related to guiding, some issues related to camera, some fringes, some optical issues, and some other stuff that we did over the course of time. So one thing that seems to be a product of choosing lithium niobate over calcite for our LEO filter is the intensity offset drifts. So the wavelength offset for the LEO filter drifts. So when we first put together LEO filter in the lab here, Steve, somewhere in the middle of the emission line, measured where 1074.7 should have been, but it's just kind of in the middle of the emission line. Then we went up to the sky and found where the 1074.7 really was. We put in a wave offset, so when we do our tuning, we knew right where to go, so we always got back to the emission line. But it turned out over the course of the Yukon mission, the actual offset we needed to put in moved. And it seems to be moving over time. This is probably something with the lithium niobate changing over time. We don't fully know. But if you look here in 2021 on December 12th, the peak brightness of these 5 points across the line is probably somewhere between these two images. Then by about a month later, it shifted to being pretty clearly on the 1079.59. Then on the 17th, we applied a correction to the wave offset to bring it back over here to the center line. And where this is going to affect you guys, if you're looking at 3-point data, if you get it right before or after we do a correction, it'll be a big change in where the peak intensity is. And that's just because we're misreporting where our wavelengths. So part of the Gaussian fit is to try to correct this and realign everything to the peak intensity. But this January 16th day, we're probably, if we did a 3-point fit, we're probably missing most of the intensity that's out here kind of off band. So this red wing won't see much. And we found that the LEO filter is drifting about 0.3 nanometers per year in 1074 and about half that in 530 towards the blue. So what we have been doing over the mission is every 2 months, we recalculate where this should be and follow the trend along. So it's kind of stepwise. A little bit after we come back online, I think we're going to do this where we basically follow this trend and every morning recompute this. So we should always be on center for data in the future. One interesting thing I'm really looking forward to was we left the LEO filter off for a year by the time we get back online. I'm not sure if this trend is going to continue linearly or jump up, but we're going to do some engineering to find out what happened when you ignore the thing for a while. But this can creep into if you need to know what the wavelength is, pay attention to this. And then here's a kind of pointing guiding issue. So Richard Martin kind of brought this up earlier. If we have any sort of spar motion or wind or something buffeting the telescope while we're doing our 30-second or 2.5-minute data collection, we're going to cause some smearing of our polarization state or smearing between those modulation states, which is going to cause the data to look bad. So on this particular day, we had 158 1074 images, of which 58 failed the pipeline's metric for what's too noisy and what has too much V crosstalk. This one was the worst one that didn't fail. But if you look in our level 1 data over here on the left for some good stuff, you're going to see the Q's and U's are somewhat smooth. There's no sharp structures in them. And the V basically doesn't have any signal at all. Maybe there's a little aerosol here, but there's basically not much. But over here on the bad data, the Q's and U's have a lot of sharp features, and we can start seeing some signal in V that might look interesting. So this shouldn't be included in the processing. It'd be good going forward in the real-time code up on the mountain if we could figure out how to either stop the Spar from shaking or align these images before we have them together, but we haven't done that.
Okay, next question.
Yep.
In your observer notes, do you ever note like windy day or anything like that?
We do.
Yeah.
I think this was actually, we're having a problem with the Spar guide, the right ascension drivetrain. So this was happening even without an external force, but the notes do have some sparse notes about wind and sky conditions, good, bad, hazy.
Wind speed is recorded at the fixed header as well.
Yeah.
Oh, okay.
So another problem we can have is that if somehow we off point and point at the disk of the sun briefly, it'll do really funky stuff to the data. So this had one, so on comp page, you have an idea. I don't know how to ask that just now. So if we get a little bit of sunlight spilling over, I think someone bumped into this bar at this point. We can do some really weird stuff to the data. So this image here, if you just looked at the intensity, you'd see a really dark intensity for the blue wing of this level 0, but 2 minutes later, it looks, a lot nicer. And without kind of going to the level 0, if you just take up a level 2 image, what you see down here, the level 2, because this was a dynamics file, which uses all the wavelengths, ends up having a lot less signal everywhere. And it wouldn't be obvious just from level 2 that actually we had some sunlight spilling over the edge of the occulter, which kind of trashed this whole measurement. Where, 2 minutes later, you get a lot more signal, looks good. And then here I just included that same time period, but in polarization, where you can see the polarization has a smaller effect because polarization mostly relies on the line center relative to the compared to the dynamics. As the dynamics 2 minutes later looks somewhat similar, but okay. So we had pointing problem, we had guiding problems, pointing problems. Another thing is if aerosols go past the telescope. We saw with Mike's presentation, the pipeline does a pretty good job correcting aerosols. But if we have a lot more dust or cloud bands or something going through, because we're doing this round robin through the polarizations, a dust particle going past will end up leaving bright, dark, bright, dark, bright, dark trail, or a cloud band going past will leave a kind of wave pattern. So you'll see some of this in the data that just probably makes it something you want to avoid using or really decide whether you want to use it. Okay, so another kind of pointing problem we can have is a doming problem. If ever the observer lets the spar point at the side of the dome, we'll see some fringing around the edge of the dome that'll show up like this pattern. Most of this didn't get processed by the level 2 pipeline, but this one did. So this extra light out here that's diffracting off the side of the dome is going to cause problems if you're looking into the level 2 stuff. So, if you're looking and see a pattern like this, that was probably the observed the edge of the dome. So one of the things we can have is a bad pixel problem, and we do a pretty good job correcting the pixels, but this was a brand new camera that we installed that we never produced a bad pixel map for. So you can start seeing where these bad pixels are and how they come up through the peak intensity. So all these little dots everywhere. So if and when we get to making the bad pixel map for this camera, this should go away in the level 2 processing, but we needed to do a little bit more to this camera. So Steve was out right before we had the lava flow that took out our road, and we added a new camera and we did a few other things, including changing the wavelengths. And we never fully processed that data, so it's not completely up to snuff like the rest of the pipeline. And then almost, as we were getting into what our next steps were, we had a lava flow and took a short break. So another problem that Mike mentioned with the camera are these glitches. So Mike showed one where we had a little fringe of the occulter sticking out past, but if you pull up any level 2 data that has some pattern where you see kind of a really bright dark pattern in the polarization, or just a chunk of the occulter moved over to the side, like we see here, report that to us. We want to, I should have found them all, but we want to find them all, have the pipeline process and remove them. That said, this week there are some that we know about. So in a month from now, after we reprocess again, we would really like to know if there are any of these, because they just do bad stuff to the processing. For a while, when Maurice first started looking at one of his favorite CMEs, there was a big hammer glitch in the data that was causing a lot of problems when he was tracking stuff. And this turns out each one of these glitches tends to come from a single read out of the 3,000 images. Where, and this, we don't actually know what's causing the camera to cause it to just move over by a couple columns. But the one where we get a big row problem seems to be something related to the cabling in the camera. So after we fix the cabling, it got better. But we bumped the cabling again, so it shows it comes and goes a couple times in the mission. Okay, so another thing Mike mentioned was we do some column corrections, but sometimes we go too far. So especially if there's a bright feature on the limb of the sun, the way the camera correction can work will cause it to cause these extra big column problems. This seems to be something shown more in polarization than in intensity, because with intensity we end up averaging out for some reason. But you can see, you know, it comes all the way through to our level 2 polarization products, but you know, you can barely make it out in the intensity products. Switching gears to some alignment and fringing problems. We had for most of the 2022, especially in the spring, we had an optical alignment problem, which we were getting scattered light on the southeast. So you get these big bands. Yes, big bands of extra light spilling over that caused a lot of problems, including for the Doppler. So, you know, this ends up, for whatever reason, getting tagged as a really strong redshift velocity, and similarly kind of causing some other problems in the polarization measurements. And this is just simply some scattered light. It's at a fairly low level. It's just at the level of what the pipeline comes through. So I don't know how to fix this in the past data, but if you're using these data products, it tends to be salt and peppery in the Q's and U's. So if you're doing your own masking, looking through the Q and U data until you find where the data goes from a nice, smooth, continuous color to kind of a salt and pepper, every other pixel is good or bad, that's probably a good place to mask, even if you're just trying to produce a velocity mask or something. And we can see, you know, it's extra bad in the 1074, but 1079 up here also shows that same scattered light in the southeast. We also tend to see these 45-degree fringes that are caused by the polarizing beam splitter and the reflected beam. So there's some sort of fringing pattern that's happening as we reflect off the polarizing beam splitter. So, and it shows up in basically all the data if you try to go down to a low enough signal, from level 0 up to level 2. But if you go, so these top images are, I think, a single image for the day, and the bottom is the quick convert. So it's a whole day's worth of data. And at that point, you average enough, and the signals have moved enough that the fringes kind of go away. But if you look down deep enough, they'll still be there. And it's not showing up very well here, but another thing we see when you get down to low signals is a curved fringe. That, especially in the 789, there'll be big arcs. This seems to be related also to an optical alignment problem. But the thing that actually made the signal go bad here was related to how we treat our Leo filter. So in order to actually make it work properly, we need to do a thermal, or we need to compensate for temperature. But our thermometer broke partway through taking this image on the upper right, and we started misreporting the temperatures to the Leo filter. So the Leo filter tried to drive way out of band to end up correcting for the fact that it was now 4 degrees cooler. The Leo filter said it was 4 degrees cooler than it was, and we pulled out a lot more noise instead of the signal, but these are all with good skies, all taken relatively close to each other in time. So maybe here's just another example of these curved fringes. It seems to be something that shows up more in the bluer wavelengths, but you can, if you drill down enough, you can see them.
And do you mind going back to the last picture?
Sure.
So I can see sort of down in the lower things, I can see these arch type patterns. Is that what you're talking about?
So it's this curve right here.
Yeah, so if you go back to that one, what I wanted to ask was,
Mhm.
there's a interesting structure in the image in the upper, on the top, in the upper right, that very curved structure, that's real, right? Or is that a,
This right here.
no, up into, up
This
to
is-
that, yeah,
This I think's real.
Yeah.
Yeah. So this, actually, it's not a very good example. Yeah, this is, I think, a real corona structure. And then this was just the quick invert for this day. So it ended up pulling in a bunch of stuff. So, you know, I started with this bad quick invert and came back to finding out, oh, this was the day our thermometer broke. But yeah, the structure up here is real. And one of the ways you can kind of see is you can just, the fringes tend to show up where the signal's really low because it's just the noise floor that's kind of there. And you know, this is a very high signal image. And I don't know, wasn't clear, but this is all level 1 data that went into this level 2 data product. And another thing we found in the last 3 weeks, we don't actually have any idea what this is, are these fine structure fringes. They seem to be all over the mission. Somehow they must be showing up because of the way we deal with our polarization states. But the way they move and act, they seem like aerosols, but they take up too much space on the image to be what we had thought of as aerosols. So this is a very open question to us, was what we're even looking at. But they do tend to even make it all the way through the processing into polarization measurements. You can see a little bit of that pattern in here in the LORI and ASA, although it shows up a lot better in the level 1 data.
Are they there all the time? Since they're observation.
They're very transient. So they seem to be there the whole mission since early in May 2021, but like the next image they won't be. There might be some in the next, you know, 2 minutes later, but they won't be in the spot. So it seems like as though something's moving, and we haven't done a good census of them, but anecdotally they seem, when the observer reports really great skies, we don't see them, and when we start to see bad aerosols coming in the afternoon, we see more of these. And I didn't mention this in the aerosols, but a lot of these aerosol artifacts tend to come in their afternoon. So where we are in Mauna Loa, in the morning we have a downslope breeze that has very clean, like pristine air, and then as the mountain heats up and gets hotter than the ocean, we start pulling up dust and some moisture from the ocean. So somewhere around 11 o'clock local time, 21 UT, we'll start seeing more aerosols. Some days are clear all the way through. Some days are aerosols first thing in the morning. But the trend throughout the course of the day, if you're looking at a day's worth of Yukon, is to tend to trend poor as we get towards midnight UT or noon our time. So you'll see more and more of these structures. But yeah, I don't know what the fine. I think we're gonna probably understand the fine fringes better in a month, just because we're only now doing the census of them. So we talked about this a little bit earlier, but because we're picking the continuum at a fixed location relative to the mission line that we're studying, we can actually we end up observing prominences in the continuum for the 706 and the 79. So these were both taken around the same time, and there was a nice prominence eruption you can see in silhouette launching through the 79 data, and it didn't look as nice as the 706. So I only pulled up one image. You know, these are coming through.
in the view graph I had about
Yeah.
the side lobes.
Yeah, so there's
Getting like the continuum side lobe that you then bring.
Yeah.
Is what makes it come in as negative, because you subtract that out as background. 706 as well. So but there's some, that prominence material you see 706 is because there's a weak prominence line. In real proximity, just within that bandpass. But that pre-filter, but
Yeah, so if you're looking at either of these wavelengths, you just want to be careful of relative prominences still. That's some headache. Another thing that we have that I don't fully understand the source of is if we have a really bright saturated set of pixels, which tended to happen when we were looking at the chromosphere, or longer integrations when we were trying to get deeper in the chromosphere, we end up, the instrument makes these, streaky patterns that are almost vertical for one and a little off 45 degrees that happen everywhere we get bright pixels. So a good chunk of our helium-1 data was kind of useless when we were trying to go deeper and look for fainter structures because it was just entirely dominated by these big, massive structures anytime there's an active region. This was part of the reason why we decided to remove the helium from the telescope when Steve was out. There's some interest now, so we might put it back, but if you're looking at the helium, you got to be wary of these things. They're just a lot of places. I guess now this is getting into some weird things that we did at some point. There was 3 days around Halloween in 2021 where the occulter post wasn't fully coming out of the beam during flats. So we ended up with this structure that we were actually seeing a dark spot in the flats, which came out bright in the intensity level 1 and dark in the level 2. If you happen to be looking at these days and see this thing on the edge, there's not much signal out there, so you shouldn't be looking there anyway, but that was related to something in the beam. Early in the mission, before August 2021, our occulter was upside down. So the level 1 data, you can see some tool marks on parts of the occulter and see this cone structure that we shouldn't see anymore, and that was causing some amount of scattered light around the occulter. We've now installed the occulter right side up for over a year, so there won't be those features anymore, but if you're looking back that far in the archive, there can be some weird stuff there. Also, it being upside down meant the radial derivative didn't work as well, so I don't think the centering worked as well before August 5th, 2021. And then we have this strange issue where we get stray light that seems to be coming in off the flats in the 706. So there's an off-centered blob of light that just seems to be there in most of our 706 measurements. We don't really understand the exact source of it. So, and then this is that same movie, but I cropped it a little bit to get rid of some of the outer field where there's more noise. And I got rid of some of the bad frames. So now we should just be seeing happy, fun polarization signals. And do you have any questions about that? This is kind of a weird just survey of things we've known. Yes.
It's
Yeah, it's to follow the question I put in the chat, and also I asked earlier. So you're summing these 16 images on site. I just wondered what sort of the instrumental jitter is between the exposures. Is it significant? Because you'd end up with a kind of smearing over those 16 images if there was some motion that you don't want.
We tend to, when things are working well and the spar isn't shaking, I think the instrumental jitter is smaller than our pixels. But when we have some sort of oscillation in the spar or due to wind or something, we'll end up seeing these structures which tend to dominate. But I don't have a quantitative number on that.
Okay.
We do have some feedback from the guider signal, don't we? Like how much jitter there is.
Yeah, so we do, the guider has a in the fixed headers, we have some guider keywords that tell you, they're hard to interpret right off the bat, but the guider attempts to make a scintillation measurement, which is a not perfect, but okay proxy for seeing in arc seconds. And then on both the drive motors, there's essentially the average oscillation, or the average, what is it? It's the average voltage that the drive motor is getting, along with the standard deviation of that. So as we see those go up, we can relate that to how much motion the guider is detecting. But so far, the best metric we have is kind of this V crosstalk, where we come in and look for how much signal is seen in the V images, and then how kind of sharp the features are in Q and U.
Okay, cheers.
And Richard, there could also be some motion induced by just the turbulence of the atmosphere. So we may have some scene effect in the day when scene is very variable and it's not very good. So it's usually not as bad as what I'm showing here, but that would also show up as a spurious signal in the polarization.
Yeah, so, and then I think the more we've been looking at this over the last couple of months, the more it seems likely that we're gonna do some sort of testing of the level 0 data before we combine it. But we haven't fully defined that yet, or whether it's just calculating the sigma of all of them, or putting in some sort. Ideally, it'd be nice to actually just realign them all between each image, but we haven't figured out what that's gonna look like yet.
Ideally, I would like to take the images as not summary
Yeah.
and do some kind of control and realignment. Then that would be ideal. But
I mean,
the suggestion to look at the signal
Yeah.
would actually be an indication of how bad
Yeah.
or good the pointing was, if it was the star or
Yeah.
atmospheric turbulence. So that at least would give us some insight on the quality of the raw frame. So I think it's something we should be prepared.
And I don't think we're gonna get more bandwidth up the mountain anytime soon, but we could make sure the stuff we send is better side.
And then the information you were talking about on pointing and scintillation, is that at least as fast as the acquisition of a single frame? So I don't know if we're getting that fast
I
enough.
think that the stuff in the header is only the primary header,
It's an average, isn't it?
the STS.
It is averaged together. It's in about 0.
Okay.
And it's only.
Yeah, that would help too, to have it at the
But-
rate of at least the single frame, if not faster. I
Yeah.
also have a request, but it's unfair of me to ask, but the stuff that the known knowns that are problems, it would be nice if there's some information when somebody clicks on a calendar date, just to have a little information there saying on this day,
So,
we had maybe the temperature of the filter was being
Yeah.
reported incorrectly or something. That would be helpful for a user. I know it's a lot of work. Anyway, I just want to put that out there. We can talk about that.
Okay, I'm gonna
Okay.
waste a minute then. So this is, not written in a way that's maybe the most useful for probably outside people, but we have a log of the changes to Yukon over time, including the temperature, probe issue was in here. And it was written fairly shorthand, so the assumption was people knew what all the acronyms stand for. But this could be something that we could figure out how to make available to Yukon users. So you can see that on September 14th, we swapped the occulter to occulter number 33 or 31. What that means in arc seconds, I forgot, but we swapped the occulter on that day. So this is something that we could also figure out how to put out there as more documentation. And,
Useful.
it's a nice little spreadsheet with tabs on the bottom so you can go between stuff. All right,
Thanks for doing that.
Yeah. Okay.
All right, well, thank you very much, Ben. So next, we're going to have 3